Welcome to today's Explainer. We're diving straight into an absolutely incredible industrial roadmap. We're going to unpack exactly how Elon Musk is merging microscopic silicon with massive metallurgy to completely rewrite the future of technology. I mean, we are talking about a scale of manufacturing that honestly almost defies logic. It's totally reshaping both how the brains of AI are built and how the physical bodies that carry those brains are forged. Let's get right into it. Here's the roadmap for today. We'll kick off with the $119 billion AI gamble, then explore the ecosystem's industrial brain and how they're compressing the chip cycle. After that, we'll pivot to the physical side, the 50,000-ton gigapress, redesigning vehicle architecture, and wrap up with unboxed manufacturing for semis. Okay, part one, the $11-19 billion AI gamble. Let's start with a number that completely shatters the scale of traditional manufacturing investments. It's a number that frankly sounds more like the GDP of a small country than a single corporate project. This staggering $119 billion is dedicated entirely to solving one single problem. It's not for a new car model, it's not for a new rocket. It is purely to build a gigantic manufacturing complex dedicated entirely to producing AI chips, a facility known as Terafab. To put that into perspective, if you literally stacked that much physical cash, it would cover entire city blocks. Nearly $55 billion of that chunk goes into just the initial phase of development alone, and that includes a $3 billion research facility currently under construction down in Austin. It's essentially a massive declaration of war against the existing semiconductor supply chain. Moving right along to part two, the ecosystem's industrial brain. Because, you see, this huge investment isn't just about making electric cars anymore. It's about feeding a very hungry, very fast-growing network. Every single branch of this empire is currently being severely bottlenecked by a global shortage of computing power. Think about it. You've got Tesla's Robotaxis needing real-time visual inference to navigate complex streets. You have the Optimus humanoid robot, which has to balance and control dozens of mechanical joints simultaneously. Then there's SpaceX, specifically Starlink, trying to put orbiting AI supercomputers directly into space to cut network latency. And of course, xAI, which requires an absurd amount of GPUs for massive generative AI training. They all demand their own specialized silicon. So to feed all of these starving machines, Terafab has set a mind-bending target of 1 terawatt of compute. For context, the entire U.S. power grid averages roughly half a terawatt. To reach that 1 terawatt goal, assuming each AI chip runs at about 250 watts, Terafab would need to crank out close to 4 billion chips a year. And to support the manufacturing of 4 billion chips, well, the required facility space jumps to 100 million square feet. That is 10 times larger than Texas, and it completely dwarfs Apple Park. We're talking about the scale of global industrial infrastructure, all housed under one single system. Which brings us to part three, compressing the chip cycle. Now, this is where the strategy really breaks away from the pack. It isn't just about pure volume. It's about fundamentally bending time and speeding up the evolution of hardware itself. In the traditional semiconductor model, things are pretty fragmented. Chip design happens in one place, wafers are made somewhere else, models are trained in a different data center, and optimization, that takes months, sometimes quarters. Terafab aims to compress all of that into a unified real-time loop. Imagine a test wafer being fabricated, thrown straight into a robotaxi in Texas, and tested against intense sunset glare. That data feeds instantly into xAI, and if the chip architecture itself is the bottleneck, they can adjust the design almost immediately. It transforms hardware iteration into something that moves almost at the speed of software updates. So this strategy basically splits into two distinct operational paths for the silicon. You have the AI 5, 6, and 7 lineups, which are prioritized for Earth, powering full self-driving and Optimus with fast response times and adaptability. Then you have the D3 lineup built specifically for space via Starlink, designed around absolute durability to withstand extreme radiation and wild temperature swings in orbit. The overall plan is to push out 100,000 to potentially 1 million wafers a month just to sustain this massive dual ecosystem. Okay, on to part 4, the 50,000-ton gigapress. Now we're shifting focus from the microscopic digital brain to the massive physical body. Because when you have chips making split-second autonomous decisions, the hardware housing them absolutely must be structurally flawless. Let's talk about a hidden bottleneck that has plagued traditional automakers for decades. Tolerance stack-up. Imagine stacking 70 thin sheets of metal that make up a car's frame, right? And each one is off by just 0.1 to 0.5 millimeters. Individually, it's nothing, but as you weld them together, those errors behave like a chain reaction. By the end of the structure, the total deviation reaches several millimeters. Doors don't close flush, panel gaps aren't even, and automakers have to spend massive amounts of time doing slow, manual corrections to fix these compounding errors. And here is the brutal but totally elegant solution. By using a gigapress, especially moving towards a monstrous 50,000-ton press, you cast large sections of the car as one single solid piece. That whole chain of 70 parts, completely erased. And because there is no chain of parts, the accumulation of error simply ceases to exist. The geometry is defined exactly once inside a high-pressure mold. That leads perfectly into Part 5, redesigning vehicle architecture. Because this goes way beyond just saving time on the factory floor. This is about building an entirely new physical foundation for the vehicle. This shift completely redefines what the battery actually does. In a traditional EV, the car is basically a rigid box carrying a heavy, isolated battery. But with gigapress castings, we get what's called structural battery integration. The incredibly stiff, single-piece front and rear castings, which have zero weak weld seams, remember, actually clamp the 4680 battery pack right in the middle. The battery literally becomes a load-bearing element of the chassis, so stress travels smoothly across the material without tearing the vehicle apart, which dramatically drops the overall weight while increasing safety and range. And this manufacturing leap is so critical, so fundamentally superior in cost and efficiency, that traditional competitors are panicking and racing to catch up. China's Dongfeng Motor is already testing massive 16,000-ton die casting systems. Hyundai is developing a 9,200-ton hypercasting program, and Volvo is deploying an 8,500-ton system. The whole industry knows that if they stick to welding thousands of individual parts, they simply won't survive the EV price wars. Finally, let's hit Part 6, unboxed manufacturing for semis. Let's look at how this exact same philosophy, erasing parts to gain efficiency, scales up to reshape the heavy freight industry. By replacing heavy traditional welded steel frames with high-pressure proprietary aluminum die casts, they are stripping away over 800 welded parts from the Tesla Semi. That removes 500 to 800 kilograms of curb weight. And in the freight world, every single kilogram you remove from the truck's weight is a kilogram you can add to your cargo payload. All of this while still enabling an 800-kilometer range. It's a massive win. Which brings us to this really cool concept of unboxed manufacturing. Instead of a long, traditional, linear assembly line slowly welding a truck together piece by piece, massive modules like the front section and rear section are cast independently in just over a minute. They're scanned with X-rays from microscopic defects, joined with the structural battery floor, and then brought together only at the very final stage. It condenses hours of tedious, error-prone welding into just a matter of minutes. So as we wrap up this explainer, we're left with a massive question to think about. We've seen how Terafab aims to create the brains, turning hardware iteration into a real-time software-like loop. We've seen how the gigapress creates the bodies, eliminating thousands of parts and millions of errors in a fraction of the time. When one single company controls both the microscopic AI brains and the massive physical bodies, moving at a speed the legacy world can barely even comprehend, what happens to the rest of the industry? Thank you so much for joining me today, and keep questioning the road ahead.